All right, so this is number 4. We're calculating the age of the universe, assuming that there's no influence with the cosmological constant, which of course would cause the universe to accelerate. At least that's what it's currently being used for. Anyhow, it's being used to explain the observed acceleration of the universe. We really don't know why the universe is accelerating its expansion, but anyhow, so we can do this. This is basically a simpler way of calculating the age of the universe. You don't get exactly the right answer, but that's fine. All right, so anyhow, the thing that we need here is we have to convert parsecs to kilometers. Okay, so there's 3.1 times 10 to the 13th kilometers in 1 parsec. So, the age of the universe is just simply the reciprocal of the Hubble constant. So we're going to use, and of course the Hubble constant is in units of, I guess I should put this, kilometers per second per megaparsec. All right, and then, of course they're all, that's the same thing with the H0 of 70, right, which of course is the accepted one, and then of course it's the same thing for H0 of 80. All right, so they want us to do it for all 3 of these. I mean, it's basically the same calculation over and over again. All right, so now let me convince you that this is indeed units of time. 1 over H0, so I'm trying to convince you that 1 over H0 is units of time. Well, you can just look at the units of this. It's distance divided by think of it in terms of distance divided by time divided by distance, right? The basic idea is the units of distance will cancel each other, and then you're going to have 1 over seconds, and so the seconds will go up to the numerator. All right, let's just look at that for just a second. All right, so I'll do the first one here. So I'm going to do this one with 60, even though that's not the they want us to do it with all 3. All right, so again, we're using this conversion. All right, so once we get the conversion exactly down, you'll see it's 3.1 times 10 to the 19th. Let me show you why that is. All right, so the basic idea is I've got to convert. So instead of converting 1 parsec to kilometers, I'm going to convert. Since this is in megaparsecs, I've got to convert 1 megaparsec. So 1 megaparsec, right? And mega just means times 10 to the 6th. 1 megaparsec. Well, it would be the same as as what it is in kilometers for 1 parsec. But then I multiply so I just multiply 10 to the 6th times what it is for 1 parsec in kilometers, 3.1 times 10 to the 13th, right? Kilometers. See that's really all I need, and so it turns out, of course, you have the same base. You just add the exponents. So 13 plus 6 is 19. So it turns out 1 megaparsec is equal to approximately 3.1 times 10 to the 19th kilometers. All right, so that's what 1 million parsecs is. All right, and then then it becomes a really easy problem. All right, so let's get a nice clean slate here, and all right. So again, here we go. So this is again number 4. All right, so I'm going to start. My first one was A. So what is 1 over H0? Right, so which remember is the age of the universe. So in the first case, it's 1 over 60, and that's of course kilometers per second per megaparsec. But see, if I convert a megaparsec, since this is in the denominator, you just put the megaparsecs in the numerator, right? And so it's really a mega, whatever megaparsecs is in kilometers, which we just figured that out, divided by 60 kilometers per second. All right. So again, if I convert the megaparsecs to kilometers, the kilometers will cancel. All right. So that's the basic idea. All right. So again, we've already converted what one megaparsec. Just to remind you, one megaparsec, is 3.1 times 10 to the 19th kilometers. All right, so really what this amounts to is dividing the Hubble constant by this each time, and that converts it to seconds, of course. So for A, this is going to be the age of the universe in seconds. I'll convert it to years as well. All right, so anyhow, it is 1 megaparsec, of course, which is going to be 3.1 times 10 to the 19th kilometers. I want you to see that the units do cancel, and then divided by 60 kilometers per second, right? And so the kilometers cancel nicely, and then you get 1 over seconds. And so this is the age of the universe in seconds. Let's see, what did I get? When I did this, I got approximately 5.16 times 10 to the 17th. 10 to the 17th seconds. All right, so that's the age of the universe if the Hubble constant, if the Hubble constant is 60 and there's no acceleration in the expansion of the universe, which of course there is, which alters the calculation. Anyhow, so when you do this, it turns out to be, what does it turn out to be? Let's see, so 1.64 times 10 to the 10th, which would be 16.4 billion years. 16.4 times 10. So of course, how am I doing that? You divide this by 60 squared, right? Because there's 60 minutes in a 60 seconds in a minute, 60 minutes in a second, so 60 squared, and then also divide by 24, because there's 24 hours in a day, and then also divide by 365, right? And that'll convert seconds into years, right? So that's that many seconds per year. All right, so anyhow, so this will be in years. All right, so again, you do the similar thing with here, let me set it up real quick so we can see that. All right, very nice. So for part B, and this is actually more like what the age of the universe is. So again, remember, it's 3.1, so you're just doing the same thing each time, times 10 to the 19th, and remember that's kilometers, divided by, in this time it's of course 70 kilometers per second. All right. Remember, this thing in the numerator is 1 megaparsec, so the kilometers cancel, and so that gives us, what did that one come out to? 4.4 times 10 to the 17th. I'm sorry, 1.1. Let's see, what does it come out to be? 1.4. Sorry, 1.4. 1.4. No, I had it right. I'm sorry. I was already changing it. I got 4.4 times 10 to the 17th seconds, right? Because remember, the answer comes out in seconds. That's to the 17th seconds. So sorry, that's supposed to be 17, not 11. So the 17th seconds. All right, and then of course, you again divide this by you divide it by 60 squared, and then divide it by 24, and then also divide by 365. All right, 365. And so you would get the age of the universe of approximately 14 times 10 to the 9th years, right? Which is, of course, 14 billion years. All right, and then let's do the last one, part C, where the Hubble constant, suppose the Hubble constant was 80. So here's for part C. So we're going to use, 80 equals 80, just to remind ourselves. All right, so again, it's the exact same calculation. The age of the universe is just the reciprocal of the Hubble constant, right? So it's 1 over 80, and of course, remember that's kilometers per second per megaparsec. And the trick here, oops, that's a PC, megaparsec. And so the trick here, of course, is to convert 1 megaparsec to kilometers. And so we do that over here. So it's going to be 3.1 times 10 to the 19th kilometers divided by, remember, you can see this megaparsecs goes up to the numerator. That's the basic idea. So there's 1 megaparsec in kilometers divided by 80 kilometers per second. All right, and so the kilometers cancel, and so that gives us, let me scroll down just a little bit here. Let's see, can I scroll just a little bit? Come on, why are we not scrolling? All right, so here's the last one. This is taking longer than I wanted it to. Anyhow, 3.1 times 10 to the 19th, remember that's the number of kilometers, divided by 80 kilometers per second. And so it turns out to be 3.87 times 10 to the 17th seconds, which turns out to be about 12.3 billion years. All right, so all right, let's work on the next one. The last problem, number 8. So in number 8, we have, actually, let me pause it and then. All right, so here's number 8. Let's look at that real quick. This is the last problem. So what's the present peak wavelength of the cosmic microwave background radiation? Calculate the size of the universe relative to the present size when the radiation was in the infrared at 10 micrometers, ultraviolet 100 nanometers, and gamma 1 nanometer. Okay, so we're going to do all of those, and yeah, so here's the equation. So the first part is to calculate what lambda max is. Remember, we're using, this is called Wien's law. So the temperature is 2.9 times 10 to the minus third, or you could say it's nanometers, that's fine too, times Kelvin divided by lambda max. And so rearrange this equation. This is, again, Wien's law. We know that the current temperature of the universe, the average temperature of the universe, is 2.7 Kelvin. So lambda max will be 2.9 times 10 to the minus third, and that's, of course, meters times, Kelvin times meters. I didn't quite fit that in there. Anyhow, that's Kelvin times meters, and of course the Kelvin cancel, and so that'll give us 2.7 divided by 2.9 times 10 to the minus third gives us 0.001 meters. In other words, the current the cosmic background radiation is at 1 millimeter. All right, so that's the. All right, so here we go. So this is how you do the relative size. It's this exact same each time. All right, it sounds really weird, but anyhow, it's whatever the current background radiation is. So that's lambda now. This is the wavelength of the background radiation to whatever the background radiation was at that some time in the past. So the first one they tell us what was it when it was 10. All right, so here are all the answers, right? The first 100 times, and then 100,000 and then 1,000,000 times smaller. All right, so you can just do these calculations